Okay. All right. Thank you for your patience. I apologize for the late start, and I just want to let you know that I uploaded the wrong version of the file to Canvas, and so this 102B 3-1 has just been updated as of 9:08 a.m. So if you downloaded it prior to that, I just need to let you know that that is outdated. So the updated version is up here now. It's mostly the same, but a few things have been changed. Okay. I guess before I get started, I believe you are all aware of the midterm exam, which is in 2 days. And so I posted this document on Thursday of last week, and this is still correct and true. And so you are allowed to have one full sheet of notes with typing or handwriting on the front and back. Also, you will definitely need a calculator, so I want to make sure you bring a calculator to class. Maybe I'll write. I don't know how to make something. Make sure to bring a calculator to the midterm exam. Just right. Is that visible? I don't know. Will people see this? How do I make sure people will bring a calculator to the midterm exam? Okay. Well, anyway, that will be on Thursday. I will also, it's a little unusual, but I will send out a seating chart, okay? I will mail out a seating chart to kind of scatter everybody around. It's going to be crowded. But we'll kind of I'll try to arrange it in such a way. And then, there'll be, probably 2 versions of the exam and so on and so forth. So anyway. So that will be the midterm. I don't know, did any of you have questions? Yeah.
The midterm in the same room?
Yeah, right here, 9 a.m. on Thursday. Okay, so same as lecture time, same location. This is where we're scheduled. So, it's like if we want a different classroom, I have to put in a request to like weeks in advance and things like that. And so, not bothering with that. This is adequate, so we will meet here. Okay. All right. Well, we'll keep moving forward. So today we're continuing on in neural networks, and we are covering back propagation. Back propagation, in of itself, is not going to be on the midterm exam. You do need to be familiar with the concept of a gradient for a neural network, and you will estimate the gradient using numeric gradient calculation. And I did an example of that in Thursday's lecture, at the end of Thursday's lecture. So, so you have to be kind of familiar with the forward feed part of a neural network, but I think that should be enough, okay? So I wouldn't stress too much about today's stuff as far as the midterm exam goes. Of course, you still need to learn today's stuff to do homework 3, but as far as Thursday's exam goes, you don't have to worry too much about it, okay? All right, so here is the diagram of our simple neural network. We've got 2 nodes in the input layer connecting to 3 nodes in the hidden layer, which connect to 1 node in the output layer. The connections are influenced by the weights. Those weights are gathered in our first weight matrix, W super 1, and then the second set of weights are gathered in our second weight matrix, W super 2. And so here they are. W1 and W2, and we can see the 6 weights arranged this way and the 3 weights arranged like this. The activation function here, we are using the logistic or the sigmoid activation function. Again, different activation functions are available, and we are using this kind of maybe for reasons of historical popularity. And here we have forward propagation. This one does not involve any bias terms. We just do x times w, and then we apply the function to that product z. We get the activated values. Once we get the activated values, we multiply it by the second weight matrix W2, and then we apply the activation function there, and that's going to produce our predicted values. Okay. If we had bias terms, we would add a bias term after doing x times w, and then or after doing a times w if we had bias matrices. So what we want to do is we want to find the set of values w in w1 and w2 that will minimize the loss function. We want to minimize the difference between the predicted values y hat and the actual values y. Okay, so our loss function is going to be the sum or the mean squared error. We take the difference between y and y hat, and we're going to square those differences, add them up, divide by n. Now, just to kind of simplify a little bit of work later, I'm going to just multiply L by n over 2, and I'm going to get J, which is pretty much the exact same thing, except it's just 1/2 of the sum of squared errors. Okay, all right, and we can see that whatever values of W1 and W2 that will minimize this will be the exact same values that minimize L, because they're the exact same function, just separated by a constant. All right, so as far as training the network goes, we need to find out the set of W1 and W2, those weights, that will minimize the sum of squared errors. And so to do this, we are going to use gradient descent, okay? And again, the idea with gradient descent is we figure out the gradient and we just take steps downhill. So we don't have to, so the traditional calculus approach would be to find the gradient or the derivative, set that equal to 0, and solve for where the gradient or the derivative is equal to 0. And here we're doing, taking a computational approach that says we're going to take the gradient and just go downhill. Okay. Issues with gradient descent is that it doesn't guarantee that we're going to find the global minimum, but it does help us find, a lot of times help us find values that perform well. But we also saw, some of the limitations of gradient descent. Depending on your learning rate, you could end up bouncing all over the place and not converge. It can also get stuck in regions where it becomes flat. Okay, so again, if the instructions for gradient descent is just walk downhill, right? But then if you're walking downhill and you hit kind of a flat region, you don't, like, which way is downhill, okay? It becomes confusing, and gradient descent can suffer that as well. So a recommendation is to start at different starting locations, and that often, it's kind of like if you drop a marble on different parts of the map, and each marble or ball or bowling ball, whatever, rolls downhill. Depending on where you drop that location, as it rolls downhill, they might all kind of converge to one spot if it's like a simple like bowl structure, or if it's, you've got ups and downs, and each of these things can end up in different local minimum. So those are just some different ideas. But as far as gradient descent goes, the algorithm itself is very simple. You find the gradient, and then you just use that to keep taking steps downhill. And that's what that's what we're going to do here. So again, here's our neural network, and finding the gradient is we want to see how does our loss function change with respect to our weight matrices. Okay, so basically if we expand out what is the gradient, right? The gradient of W1 is going to be basically the matrix of partial derivatives. How does the loss function, our loss function is called J, how does that change with respect to the first element in W1? How does that change with respect to, W1 sub 1, 2, W1, 3, W2, 1, W2, 2, and W2, 3? And so notice that the dimensions of this gradient, the dimensions of this thing, are the exact same dimensions as W1 itself, right? So if I go back to what does W1 look like? It is a 2 by 3 matrix with the terms 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3. And the gradient is the exact same dimensions. Same thing applies to W2. W2, the matrix W2 is a 3 by 1 matrix, and the gradient, dj dw2, is also going to be a 3 by 1 matrix. All right? And this is important because the way gradient descent works is it says take your current value of your matrix, say W1, and then add a negative constant times your gradient. And so if the gradient isn't the same dimensions as the original matrix, you can't just add those two together, right? So to add two matrices, they have to be the same dimensions. So if W1 is 2 by 3, and we're going to say add the gradient also has to be 2 by 3, so that you can just add those two matrices. So that's a helpful thing to keep in mind, is that the gradient of any scalar with respect to a vector matrix is going to be a vector matrix of the exact same dimensions as the original thing. Okay. If we had bias terms, we would also calculate the gradient of J with respect to the first bias matrix, or the gradient of J with respect to the second bias matrix. I'm not doing that in today's lecture. This is going to be assigned to you in, it says future, but I guess it's the homework assignment that's just been released, homework 3. Okay, so that's that. Okay. All right. Well, so let's start with figuring out the gradient of our loss function with respect. We're going to kind of work backwards. We're first going to find it with respect to the second weight matrix, and then we're going to work backwards and find it with respect to the first weight matrix. Okay, and that's basically what backpropagation is all about. Backpropagation is how does this output change with respect to changes in kind of the previous layer, and then how does that how do those values change with respect to changes in the previous layer, and so on and so forth. And even if you have a very deep network, you just kind of keep working backwards. It's a lot like applying the chain rule in calculus. You just kind of say, well, how does it change with respect to this thing? And this was the result of another function, so you have to apply the chain rule, so on and so forth. Okay, so we're going to start off with defining our loss function, and we said our loss function is basically the sum of squared errors times 1/2. So we have the actual value y sub n minus the predicted value y hat sub n. How does quantity squared and the sum of this? All right, well, the derivative of a sum is also the sum of the derivatives. So I'm going to just bring the derivation sign inside here. And now that I have this, okay, well, I've got a quantity squared. The derivative of that is I bring the 2 down, and now I have yn minus y hat sub n. And then we apply the chain rule. We ask, does yn change with respect to W2? And the answer is no, right? Yn is our actual values in our data, and it doesn't change with, if I changed my weights, does that affect the actual values? No, it doesn't. But our predicted values do. Okay, our predicted values y hat sub n, if I do change the weights in this second weight matrix, that does affect our predicted values. Okay, so looking at this, I have a negative sign times y hat sub n. So I'm going to multiply, using chain rule, I'm going to multiply this by -1, and now I have, and then I have the derivative of y hat sub n with respect to w2. All right, is this okay? So we're kind of applying the chain rule, and we're saying, okay, well, what changes with respect? If I change w2, what else changes? And so far, the only thing here is that the predicted values y hat change. Okay, so distributing this negative sign, I'm just going to multiply the -1 out here, and then we look again, kind of looking at forward propagation. Okay, how does y hat change with respect to w2? Well, we can ask, well, how does y hat change with respect to kind of its previous, where we see that y hat is the result of applying a function to z3. And then we can ask, how does z3 change with respect to w2? So that's what we're going to ask. We're going to say, how does y hat change with respect to z3? And then we'll split that and say, how does z3 change with respect to w2? Okay, so now I'm going to kind of break this derivative into these, these derivatives here. So we can do this, right? Okay, so again, y hat is the result of passing the value from z3. This should be y hat sub n as the result of passing z3 through this function, through the activation function. So the derivative of y hat with respect to z3 is the derivative of the activation function. So I can just say y hat is equal to f of z3, then the derivative of y hat with respect to z3 is just f prime of z3. Okay, and I can just kind of leave it like this. I can further expand that, and I can say, okay, well, if f is the function, the logistic function f of t is 1 over 1 plus e to the negative t, then what is the derivative of that? Okay, so using kind of quotient rule, if f is u over v, and we say f prime is u prime v minus uv prime over v squared, then this is what we'll say. I've got u is 1, and v is 1 plus e to the negative t, and f prime is going to be u prime v minus uv prime. Okay, so this is 0, and then here I've got 1 times the derivative of this, which is going to be negative e to the negative t over v squared. Okay, so I put this on the bottom, and now I have this. Okay, and so the derivative of y hat with respect to z3 is going to be f prime of this, which is going to be equal to this quantity. So I'm going to just take this, and I can plug that into here, and just kind of for simplicity, I'm going to just leave this as f prime of z3. Okay, so this is what we have. Okay, so we're going to replace this with f prime, and we'll make a note to ourselves that f prime is equal to this. Okay, so this is the derivative of our loss function j with respect to our second weight matrix w2, and so far what we're saying is that it is the difference between the actual value and our predicted value multiplied by f prime of z3 times the derivative of z3 with respect to w2. So how does z3 change with respect to w2? Okay, so far so good? Is this okay? All right, well, let's take a look at this term, and we say, okay, well, what is the relationship between z3 and w? So the matrix result is that z3 is an n by 1 matrix, and this is the result of multiplying our A2 matrix, which is n by 3, with our weight matrix W2. Okay? And if we take a look at just one of the values within this matrix Z3, we can do Z sub n. Okay, Z3 sub n. Okay, this is just a one by one scalar value, right? Because the Z matrix, there's n of these observations, and basically we're just saying, okay, let's look at the very first observation. Okay, the very first observation is the result of looking at the first row in our A matrix, which is going to be there's 3 values there, and we're multiplying it by our 3 by 1 weight matrix. Okay, so we're just looking at one value here. Okay, so maybe I'll pull up last week's lecture. So if we think about, multiplying A times W, okay, here let's just say, let's look at just this first value. This first value times this first column results in just this one scalar value. Okay, this will be Z sub 1. Okay, Z sub 1. All right, or we could just say, let's look at only the second row, and then that will result in just only the second row here. But that's what we're going to do. Okay, and that will kind of make our lives a tiny bit easier by just only focusing on one row. Okay, and effectively, at the end we're going to sum everything up, but here we're just going to look at one of these rows. So if we look at just one value here and we say, okay, how does this change? All right, so this is a scalar, and then it's the product of kind of two matrices multiplied together. So if you recall kind of our derivative rules, all right, so basically this is what we have going on here. I got a times a W, and we're asking what is the derivative with respect to W, right? So basically I've got an here I got X transpose W, and the derivative of that is going to be X, but now I just have A times W, so the derivative of this will be A transpose, okay? So, because this is the product of looking at the nth row in A, so we're looking at the nth row, and it's A sub n times W2. And what is the gradient of this with respect to W2? It's going to be A sub n transpose, right? So basically, I've got this. This is what we're calling A sub n times W. What's the gradient of this with respect to W? It's going to be the transpose of this thing, which here is A, but in this case it's the transpose of that, which is going to be AN transpose here. Is that all right? Okay, so this is it. This doesn't change with this itself doesn't change with respect to W2, and so now I will plug that in here. All right, so I've got the gradient of this with respect to this, and this is what I have here. Okay, so kind of just taking this, and I'm going to replace this term with now AN transpose. Okay, so this is the gradient. The gradient of J with respect to W2 is I take these values, and if we take a look at the dimensions of these things, y sub n is a scalar, minus y hat sub n, that's also a scalar, and then f prime of Zn3, okay, Zn3 is a scalar, and so this whole thing is a 1 by 1 scalar, and I'm multiplying it by AN transpose. This is a 3 by 1, and then once I do this, I'm going to sum up across all n values. Right? So effectively, if we look at this, I'm just taking this and I'm going to transpose this row, multiply it by a constant, and then I'm going to sum up across all n rows. So I'm going to take each of these rows, transpose them vertically, so they're 3 by 1, and then I'm going to sum up across row 1, row 2, row 3, all the way through row n. And the result is going to be a 3 by 1 matrix. All right. So the result of this, we want it to be 3 by 1, and currently this aligns. Now, that's fine. We have a summation, okay? And we could stop here and this would be correct. But we can also take advantage of the fact that when you do matrix multiplication, depending on how you have these things aligned, you can do the summation, right? So, for example, basically, right now I've got A2 transpose. Okay, well, here. So A2. Let me just double check what A2 looks like. Okay, A2 looks like this, right? Got A11, A12, A13, A21, A22, A23, AN1. Right? And then if I transpose this, okay, now I'm going to have right, so this is our transpose. And basically what we want is we want to get, when I say do the sum, we want the sum of basically I'll call this J1, and then sum over J of 2. Right? So we basically want to take this whole thing and we want to apply a sum to it. And we want to apply a sum to it. And we want to take a sum to this, and we're basically going to get a 3 by 1. That's kind of what we're doing here, right? So we're going to take basically each of the nth row, we're transposing it, okay, and then we're going to sum across all of the different n's, okay, and when we do that, we're going to get basically this thing, okay. So we can kind of, we can apply sums to this, but can we do something creatively with matrix multiplication? Is basically what I want to know, right? Now, if I just say, okay, well, let's just drop the subscripts. Okay, let's just drop the subscripts. If we do this, all right, it doesn't work, right? Because I've got an n by 1. If I drop the subscript here, I've got an n by 1 here. This is n by 1, and this is 3 by n. Okay, and so the way it's working right now, basically I'm also multiplying this by a scalar, y n minus y hat n. I've got so this is a 1 by 1 scalar, and then f prime of -3. This is also a 1 by 1, and I can multiply these by these scalar values. That's no problem. Okay. I multiply this by scalar, this by scalar, this by scalar, and then we get the sum of all of those things. That's no problem, but if I wanted to kind of take advantage of the matrix multiplication, this is not going to work. So what I can do is I can say, well, you know what? While it's in scalar form here, okay, I could just take this one term and I could bring it over here. Okay, I could bring it over here, right? While these are scalars, this is a 1 by 1 scalar, this is a 1 by 1 scalar, and this is a 3 by 1, I could kind of rearrange these terms here. And we would agree that these two things are exactly the same. Okay. And then now, look at this. I can now drop the subscripts, expand them, right? And so this is going to be a 3 by n. This is going to become n by 1. And here I'm going to have to multiply this by n by 1. And so this will become, we'll do element-wise multiplication. And this is a 3 by n. And this is an n by 1. And now we can multiply this. Because if I take this and I multiply it by basically a bunch of 1s here, okay, this whole thing times this will end up this, right? And this whole thing times this will end up this, and this whole row times this whole column will end up this. Okay, all I'm doing now is I'm going to say, okay, you know what? This is going to be the product of y minus y hat times f prime of, this is z, all right? And this one is y minus y hat times f prime of z2, and so on and so forth, okay? And if we do this, then we will get the appropriate product that we're looking for. All right. Is that okay? So I could have stopped here. But I can take advantage of matrix multiplication and say these values are going to be exactly the same if I just, instead of looking at just the nth value in A, I can take a look at the entire A matrix, and when I do matrix multiplication, it's going to basically do that summation operation. Right, and that's by kind of taking a look at just, if we look at one of the values, right? If you try to just drop the n subscripts, these dimensions don't line up. But if you take a look at one of the values, you can say, okay, well, I can rearrange these terms, and then once you rearrange those terms, because these two things are exactly equal, now we can drop the subscripts, expand them, the dimensions line up, and we get the appropriate thing. Okay, so this is n by 1, this part is 3 by n. When you multiply those, you get a 3 by 1. All right, and so this is going to be the gradient of our loss function with respect to W2. Let me go ahead and give you your first view quiz answer for today. The first view quiz answer for today is the letter A. A as in apple. I think I have it mislabeled on, I think I've called this week 3 Monday. I need to rename this, huh? Week 3 Tuesday. Is that right? I think that's right now. Okay, week 3 Tuesday, lecture view quiz. First letter is A. A as in apple. A as in apple. Okay, let's, so we have the gradient with respect to our second weight matrix. This simplifies to this, and we have, this is a 3 by 1, and we're going to call this, the Welch Labs video calls this term delta 3, and we keep this because we use it again later. And that's what we have here. All right, so now we can say, well, so we figured out the gradient with respect to the second weight matrix. What is the gradient with respect to the first weight matrix? So we're going to kind of do this. We're going to do, okay, what is the gradient with respect to the first weight matrix? And as far as up to this first set of steps, these are the exact same steps when we said what's the gradient with respect to W2. kind of the expansion of this is exactly the same. You know, we say, well, what changes when you change W1? Well, the only thing that changes when you do W1 is y hat, and so we expand this out, and then we say, well, how does y hat change with respect to Z3? And it's f prime, and then now we're going to ask, how does N3 change with respect to W1? So again, similarly, we're going to ask, how does it change with respect to W1? Well, now we're going to ask, how does Zn3 change with respect to A sub n, and how does A sub n change with respect to W1? Okay, for the previous work, we said, how does Zn change with respect to W2? Okay, well, here, now we're going to say, well, Zn, now we're asking, how does Zn change with respect to An? So if Zn is the product of A2 times W2, the gradient of this with respect to A, changes in A, is going to be W2 transpose. So looking at our table of gradient relations, now we have this thing, because we're asking, how does it change? So I know it's confusing because we've got the W, but we're asking, how does it change with respect to kind of the first term that's being multiplied? How does it change with respect to A? Okay, the change with respect to A is going to be this term transpose, or this term, and basically that's what we've got here. So so how does this change with respect to A sub n? This is a 1 by 3, so the result of this is going to be W2 transpose of 1 by 3. So I'm going to plug that in for this spot. Okay, so the way Zn3 changes with respect to changes in An is going to be W2 transpose, so I'm going to plug that in right here. So we plug that in, and we have this. So again, at this point, we still have, we're looking at just the nth observation, and this is a scalar. This is a 1 by 3, right? There's no subscript n because it's the same for the weight matrix. W2 matrix is the same for all values. And we're going to ask, how does this thing change? How does An2 change with respect to W1? Okay, and again, An2 is the result of applying a function f to Zn2. Okay, so kind of looking through our functions, An2 is the result of applying a function to Zn2. So I'm kind of just going backwards through my slides here. So what is the gradient of this with respect to this? This is just going to be f prime of this. Okay. Now, one thing to note is that this is a 1 by 3 matrix. Okay, so already we're running into some dimensional issues. Okay, because I've got a 1 by 3 transpose, and I'm trying to multiply by 1 by 3. So how do these elements align? We're going to have to do some element-wise multiplication, because you can't just, if you do a 1 by 3, and this is W21 and W22 and W23. How do I multiply that by Zn? So I got Z11, Z12, and Z13. How does this work, right? Well, we're going to have to do some element-wise multiplication in a moment. Okay, we're going to just do this term times this term, this term times this term, this term times this term to preserve its 1 by 3 structure. But that will be in a moment. We won't worry about it just yet. Now, the question, though, is what is this? What is the derivative of Zn3 with respect to W1? Okay, So if we look at this, okay, so imagine we're looking at just the nth row. We're just going to look at the nth row in here. So let's look at just this first row. What is the dimensions of this first row? It's 1 by 3, right? 1 by 3. We've got 3 values in it. And we're asking what is, and we're saying, okay, well, the way we got that was we took this first row in X, which is 1 by 2, and we're multiplying it by this 2 by 3 matrix. Okay. So if we look at just that first row in X, which is this, and I multiply it by our W matrix, which is 2 by 3, I'm going to get this first row in Z. Okay, that's what we have, right? First row in X multiplied by this 2 by 3 matrix gives me that first row in Z. And we ask, okay, how does Z change with respect to changes in W1? This is a bit of a weird thing, right? How does this change with respect to this? Okay, well this is a little bit weird, but what would happen if I added a tiny little epsilon to this first term here? Okay, what would happen if I added a tiny little epsilon here? The amount it would change by is this value right here would change by epsilon times x sub n1, right? So this would go up by x sub n1. Okay, what if I added a tiny epsilon to the second term? Okay, well, this value here would change by x sub n times the epsilon. Okay, or xn1 times the epsilon. What would change if I added an epsilon here? Okay, it would change by x sub n1 because this thing would change. Okay, if we look at any of the values in the second row, what would happen if I added an epsilon here? Okay, it would change by x sub n2 times that epsilon. What would happen if I added an epsilon to this? It would change by x sub n2 times that epsilon, and similarly something down here. Okay, so if I change any of the top values in the top row with an epsilon, it would change by a product of x sub n1. If I change any of the values in the second row by epsilon, it would change by a product of x sub n2. So the derivative of this matrix with respect to this is going to end up being a 2 by 1 matrix, and it's going to be the transpose of this row. So we end up getting a transpose. It's going to be x sub n1 on the top and x sub n2 on the bottom. So we're going to say the gradient of the nth row in Z with respect to W1 is going to be the nth row in X transpose. Okay, so I'm going to just end up getting basically this thing just transposed. Okay, and again, we have this weird set of dimensions. Okay, this doesn't quite work out if we just leave it in this form. So if we think about, okay, how are the terms related? Okay, I can have element-wise multiplication between W and our Z's here, our F, I guess these are F prime, right? So we're going to preserve this. This part will still be a 1 by 3 by using element-wise multiplication. So if I take this and I get element-wise multiplication, I'm going to get W1 times, I guess this is F prime of this, and F prime of this, and F prime of that. Now I'm going to get I get one term. This is just a scalar value here. The second value times F prime of this, and so on. Okay, so that preserves the 1 by 3 nature of that product. And again, if you look at the individual values within here, and I didn't expand this, and I hope that's okay. Again, the individual values in here, if you look at each of them, you can find each of them by kind of rearranging this term so that it ends up becoming a 2 by 3 matrix. A 2 by 3 matrix. So we're going to have this. Okay. So right now, this is the summation across all n rows. All right, and we're going to take each row in X, transpose it. We're going to take each value in Y, and then we're going to basically take each row in X. And so when we do that, we get a bunch of, this thing multiplies out to be a 2 by 3, and that's the 2 by 3 kind of gradient for that one observation. And we've got n of these observations, and so you can imagine in your original set of X values, right, you got x11 and x12, x22 and x21, and x22, and so on and so forth. Right now what we have and I'm going to just basically take this first row, I transpose it, I'm going to multiply it by, and then this whole thing is just a 1 by 1 scalar. This is y sub n minus y hat sub n times f prime of Cn3. So this is just a scalar. W2 transpose is well, I have actually here. W2, W1, W2, and these are all, and I've got f prime of Zn2. Again, this is just the nth row. The nth row of this is f prime of this. Okay, and when I kind of do W2 element-wise f prime of Zn3, or Zn2, I basically get just this is a 1 by 3, right? So I'm going to get a W times a f of Z, and a W times an f of Z, f prime of Z. So this is, for one observation, I'm going to have basically this, right? W f prime of Z, W f prime of Z, W f prime of Z. And so when I do this, when I multiply these two together, I'm going to get a 2 by 3. Is that okay? And that's just for this one observation. Okay. I do the same thing for this thing, and this will also produce another 2 by 3. Okay? And then this, the next observation will also produce a 2 by 3. And then we're summing them. So basically this one turns into a little 2 by 3 sheet, and then I add that to the next 2x3 sheet and the 2x3 sheet. So the final thing is I get the summation of a whole bunch of these kind of 2x3 sheets on top of each other, 2x3 matrices. All right, is that okay? And again, we can try to simplify our work by taking advantage of the matrix multiplication. So I can say, well, what if I just, instead of looking at the nth row, what if I just took the entire X matrix? Okay, well, this becomes a 2 by n. This remains, now I'm going to have n of these scalar values. And so we say, well, how does this work? Okay, well, I'm going to get an n by 1, and we need to kind of preserve this n by 1 dimensionality. So this becomes n by 1. And that's actually familiar to us. This is delta 3. And then I can multiply this by 1 by 3. So note there's no subscript here. W2 is the same, so this is not going to get multiplied by n. All right? And then over here, we look at all n rows here, and this is going to become n by 3. And the dimensions line up, okay? This element-wise multiplication becomes n by 1. Multiply this by a 1 by 3. This is going to become an n by 3. This over here is n by 3, so I can do element-wise multiplication to kind of preserve the n by 3 nature. We're going to multiply this by the transpose of x, which is 2 by n. So I have a 2 by n multiplied. This whole thing is n by 3, and the result is going to also be 2 by 3. All right. Is that okay? And so this is kind of our final result here. So, if you kind of take all of these terms and pay attention, again, here we're going to get 2 by n times an n by 3 at the end. All right. And again, this is why I always recommend putting little dimensions underneath your matrix. Otherwise, it's going to get confusing as far as how are these things supposed to multiply together. And so the final result of the loss function with respect to W1 is a 2 by 3, which is what we want. We want a 2 by 3 matrix at the end. All right. So we've got this as a gradient. And okay, so this was the hard part. And now what we have to do is we have to turn it into code so we can do it. Okay. And so it feels like, okay, well, how do I turn this into code? All right. It's actually quite straightforward. Turning it into code is the easy part, believe it or not. Okay, so here we're just gonna look at each element, and I'm gonna just write corresponding code for it. Okay, and I think when you look at the code compared to the mathematical form, you'll say, oh yeah, that's exactly what you're doing, right? I guess before I get too far, let me give you the second view quiz answer, and that is the letter B. B as in bear. B is your second view quiz answer. Okay, so just to kind of keep things simple so we can kind of plug values in, I'm going to create a function for the sigmoid or logistic function. And we're going to say anytime I plug in a value z, just do 1 over 1 plus e to the negative z. Okay, I know I have a t here, but that's it. Okay. Let's bring in our data, our X matrix, kind of the original data set that I think we started kind of playing around with. Is we got our X matrix and our Y, and we have 3 observations, n rows. So I'm going to say, okay, here's my matrix X, here are the values Y. And in order to kind of, for our function to work, remember the outputs, the y hats, is the result of applying sigmoid to our thing. And the sigmoid can really only output values between 0 and 1. So I'm going to take my values 75, 82, 93. I'm going to just divide them by 100. So I get 0.75, 0.82, and 0.93. That's just so that everything has a range going from 0 to 1. And then as far as the x values go, I'm going to take the first column and divide by 10, and I'm going to take the second column and divide by 5. I could have also divided by 100 or divided by some other constant. It didn't matter, but I just said, let's just take the column and divide by the maximum in the column. And that's what I did to x. Okay, well, and to kind of maintain flexibility, rather than coding in, I've got 2 layers in the input layer, 3 layers in the hidden, 3 nodes in the hidden layer, and 1 node in the output layer. I'm going to just put in variables here. I've got input layer size 2, output layer size 1, hidden layer size 3. And that way I can kind of change these variables later if I wanted to. So as far as the forward feed goes, I'm going to, remember I just do x times w gives me z2. So I'm going to do x times w1 gives me z2. I applied sigmoid to z2, and that gives me a2. I do a2 times w2, and that gives me z3. And I apply sigmoid to z3, and that gives me y hat. So I'm just taking the math that I've written out here, and I'm just turning it into code. And I think this is straightforward and easy for us to see, right? Okay. What is our cost function? Our cost function j was y minus y hat quantity squared, and we summed that up, and we multiplied by 1/2. So I got 1/2 times the sum of y minus y hat squared. Right? Also, I think no surprise here. Right? This is how we're calculating our cost. And so right now the cost between the actual values y and our predicted y hat is 0.0153. Okay, what is the derivative of our activation function? So this is just, I'm on slide 37. I just said, okay, what is the derivative? F prime is e to the negative z divided by 1 plus e to the negative z squared. So going back, e to the negative z divided by 1 plus e to the negative z squared. Okay. The gradients, remember, we did all of that work and we came to the solution that the gradient is a2 transpose minus y hat element-wise multiplication f prime of z3. And so we're going to call this thing delta 3, and this is the quantity of negative y minus y hat element-wise multiplication, so just the regular star, times sigmoid prime applied to z3. And then the derivative dj dw2 is the transpose of a2 matrix multiply delta 3, okay? This part being delta 3. Is that okay? So this is just, it felt like a lot of work to get here, and it was, but once we got it, turning it into code actually isn't a huge leap. Okay, what about the gradient with respect to W1? Again, it was kind of a bit of work to get to this point, but once we got to this point, well, it wasn't too bad. So delta 2 is delta 3 times W2 transpose times f prime of z2. So I got delta 2 matrix multiply W2 transpose times sigmoid prime of z2. And then dj dw1 is x transpose delta 2. That's what we got here. Okay, so how do we do gradient descent? Well, for gradient descent, we just start off arbitrary locations for W1 and W2, and then we just say take steps downhill. So I'm going to just randomly fill in my W1 and W2 matrix with just random values of random values. So I'm going to say set seed 1, W1 will be random values, 6 random values, and W2 will be 3 random values. And I say arrange them in a matrix, right? Arrange 1 by 2 by 3. Input layer size is 2, hidden layer size is 3. arrange the three values in W2 to be 3 by 1, hidden layer times output layer. And then to kind of keep track of how our cost function is doing, I'm going to just create a vector called cost history. And this is an arbitrary value. I kind of cheated. I already knew kind of what's a good value here. But again, this is just kind of the step size. When you do gradient descent, you just multiply the gradient by a constant factor, a positive constant, and that will be your step size. Sometimes you have big step sizes, sometimes you have little step sizes. This step size kind of works. Okay, and this is the entirety of the gradient descent algorithm. It looks kind of like a lot, but also it's not. This part up here, this is the forward feed. We take our current values of W1 and W2, and we say, what are the predictions that we would make? What are the y-hat values using our current values of W1 and W2? So how do I get that? I do x times W1. I apply sigmoid to that result. I take that result and I multiply times W2, and I apply the sigmoid function there. I could simplify this into just one line if I wanted to, but I think it's a little bit easier because we can see all of the forward feed steps here. All right, and then just for our sake, we're going to calculate the cost between y and y hat. Okay, we're going to say how different is y from the y hat values, and I'm going to keep track of that in my cost history vector. But this line is actually not necessary if I want. Okay, now that I have my y hat values, I can calculate the gradients. Okay, the gradient is basically I find dj dw1 and dj dw2 using the formulas that I have. I say, what's the difference between y minus y hat, sigmoid times sigmoid prime times a2 transpose, and then I take that and I do times w2 transpose times sigmoid z, and I multiply that by the transpose of x. This gives me the gradients of the loss function with respect to w2 and the gradient of the loss function with respect to w1. And so once I have the gradients, I do gradient descent, which says take our current weight matrix, W1, and subtract off a scalar times the gradient. Take our current weight matrix, W2, and subtract off a scalar times the gradient. Okay, so here I'm updating both matrices at the same time. I've got a W1 and a W2 matrix. I've calculated the gradient, and I subtract off a scalar at this point. And once I do that, that's one iteration. That's one step downhill. And I do this again. And here I say, do this 10,000. Find which way is uphill, take a step in the opposite direction, downhill, and take another step, take another step. Every time you take a step, recalculate which way is uphill and go in the opposite direction. Do this 10,000 times. That's what we're saying. Okay? So all of this part is part of calculating which direction is uphill, the gradients here. And in order to calculate which way is uphill, you have to find out what your current predictions are. And that's what that's all about. So this is take steps downhill, and to take steps downhill, find the way uphill. And that's all we're doing. That's gradient descent. And if I run this, these are the coefficients that result at the end. This is my W1 coefficient. These are my W2 coefficients. The coefficients basically are uninterpretable. These don't really have any significant meaning to us, okay? Because what is the meaning of W11? I have no idea. What's the meaning of W22? I have no idea, okay? It doesn't really matter. What matters, though, is that we're making good predictions. So if I say, what is the prediction you're making for the first observation? The prediction it's making is 0.7499998. What is the actual value? The actual value is 0.75. What's the prediction it's making for the second value? 0.82005. The actual value is 0.82. What prediction is it making for the third observation? 0.92989. and the true value is 0.93. So it's making good predictions, at least for these 3 observations. I mean, this is a silly training data set, but we have that, okay? And we can see the cost. It started off here, dramatically drops. It hits a bit of a flat location, and then it finds some location and starts dropping again. And then now it seems pretty flat. If you take a log of this, we can see, okay, dramatic drop. It kind of slows down. And then even though it looks flat here, there's actually a steady decrease. It's kind of like it's being multiplied by some constant factor there. And that's basically how a neural network works. All right, it's just some matrix operations here. All right, so was any of this code mysterious or seems kind of too crazy? I don't think so. Right? It's a little bit hard and challenging to think about how do you even get here in the first place. But once you get here, it's actually not that difficult as far as what are the operations being done. And we're just really multiplying matrices, we're applying some kind of function, and so on and so forth. So let's take a look, and I want to take a look at the Mnist handwritten digits data set. So just curious, how many of you have heard of the Mnist data set? So just one of you? Okay. All right. Well, the Mnist data set is kind of this very very popular and very famous and useful data set. And basically, it is basically, this was kind of in the, I guess, late 80s, early 90s. The post office said, you know what, we need to get better at sorting mail by hand. Okay, or not sorting mail by hand, but sorting handwritten letters, right? So you write an address and stuff. And they said, can we look at this zip code that people write, the 5-digit zip code, and can we get the computer to recognize what this is, and it can sort it, so we don't have to have humans doing this. And that kind of prompted this Mnist thing, and so they created this data set of 70,000 images. And I've linked. So if you search for Mnist data, you're going to end up finding all kinds of sites. This is the original data set, okay? 70,000 images, okay? Each image, so some poor grad student or some poor student, maybe an undergrad or somebody had to scan in all of these letters and then crop them into this perfect little 28 by 28 grid, and then label. This is an 8, this is a 9 or 7, and this is a 3 or something, right? And they were able to, they know what it is, because if you weren't sure what the zip code actually read, you could look at, like, okay, what is the city name here? And we go, okay, we know the city name, right? This is Los Angeles or Beverly Hills. Okay, so the digits are 90210, and then you could figure this out, right? Is that, like, are you guys familiar with Beverly Hills 90210? Is that like or I don't know, at least, or UCLA 90095, right? And like there's certain zip codes that were kind of made famous, but I don't, maybe Beverly Hills isn't famous anymore, but you have these zip codes, and so they know what the labels were supposed to be, and then they labeled 70,000 of these images, okay? And they're perfect in that they're 28 by 28, and there's nothing else, so these are just kind of beautiful little data sets, okay? And so you can download the original images and you download these things. If you download them on a Mac, you have to run g-unzip. Okay, they are zipped up in a .gz. So on Mac, you can use terminal. You find the location and you type in g-unzip or gunzip, and then the name of the file. And so in this case, it'd be g-unzip train-images-idx3-ubyte.gz. Okay, and then you would unzip train-labels.idx1-ubyte.gz. Okay, if you are on a PC, you would probably need to download this program called 7-zip. I mean, there's other things out there, but 7-zip is free and it's high quality and it's good. And you can right-click and unzip the file. Right. So I've done this on my computer. All right, and so the data is I've unzipped this the GZ files into these ubyte files, and you can see, you know, there's quite a lot. So zipped up, it's like 9 megabytes. Unzipped, it's like 46 megabytes. Okay, and what I've written some scripts and I've uploaded them. I've got Mnist load data and Mnist neural network.r, and so we're gonna do this. All right, and so don't worry about this, but this is how you would read in the thing. It basically reads in this binary information. You might need to change the path. So my data is located in a folder inside called Mnist. If you decide to put the script and the data in the exact same folder, then you would have to kind of change the relative path. But anyway, and then you can load in the data that way. All right, so let me load this up. So we'll load in, whoops, can't open the connection. Okay, there we go. So you might have to make sure your working directory is correct. So what I'll do is we'll look at the first image in our data set. The label is a 5, and if you load up the data is just a vector of 784 values. It's a 28 by 28 pixel image, right? So if you do 28 times 28, you get 784. And the data is just this vector of 784 values. And we can see the numbers go from 0, and then the biggest number that we would possibly see is 255. And in this image, it's 253. And basically, if you arrange this into the thing, this is what it looks like. Okay. This is our image. The 784 values can be arranged into a 28 by 28 grid, and this is the image that we have. The 3 blue 1 brown video shows a very good depiction of this. Jeez. Okay, we got to sit through an advertisement for Soylent. All right, here we go.
When I say neuron?
Oh, you know what? I don't want to get a copyright strike. Let me pause the video, okay? So if you're watching on YouTube, you've got to, you're gonna have to watch this video on your own, and then I'll, when I'm done playing the video, I'll resume recording. Okay, so we'll continue on, and I just played like a little video clip from around 2 minutes and 40 seconds to around 5 minutes and 40 seconds. But the idea here is, yeah, we've got 784 values, and if you arrange them in this 28 by 28 thing, it looks like an image, and we can look at basically any other image in our data set. we can look at the second image, and it's labeled as 0, and we can say, well, what does that look like? And yeah, this looks like a 0 here. Did you have a question?
So is this how like actual image recognize it?
Yeah, actual. So this is like the very, very clean data set, right? It's kind of like when you learn linear regression and we give you like 4 data points and we say fit a linear. Like this is about as clean as an actual image data set goes. And yeah, now on your phone, you can say, show me all pictures of a dog, and it will pull up images of a dog. And at its core is a neural network is being run for image recognition, and that's what's happening. But it's much more complicated. So with this data set, with a data set about as clean as this one comes, then we can create a very simple neural network. I'm going to just create a neural network with 1 hidden layer and I think 30 nodes or something, and I'm going to get something around like 93% accuracy on a very clean data set like this. Now, if I try to use such a simple neural network for real life data with images and stuff, it's going to perform much more poorly. But if you just kind of take the same structure and just make it deeper, okay, maybe do a couple things. There's like convolutions and stuff like that, dropout layers and stuff. You can get a lot better kind of image recognition performance. But at the core concept, the structure is the same, right? It's kind of like if you understand how a combustion engine works, a simple 4-stroke combustion engine works, you can just take that same thing and make a better version of it, a high-performing version of it, and you can now, you have a race car, okay, right? And that's basically all we're doing, is we're just taking this simple piece of technology and we're just making it bigger and stronger, and that's kind of how modern neural networks that do real image recognition are powered by. Okay, obviously better than our thing, but this gives you an idea. Okay, so anyway, this is we're just taking a look at our data set. The next image is labeled a 4, and we can say, all right, and again, here are the 784 values. These 784 values correspond to a 4, and when you look at it like this, it's like, that doesn't look like the number 4, but when you arrange it into a grid, you go, oh, okay, I can see how this is a 4, right? And so what we need to do is we need to vectorize or turn the output into this structure with 10 nodes in the output layer. Why do we need to do that? Okay, because you might say, well, why can't I just have one node in the output layer, all right? And if this node is a 0, it's a 0, and if it's a 9, it's a 9, and if it's a 7, it's a 7 or something. And even you can do, and we could do some kind of thing to kind of scale it down. The reason why you can't just have one node is because how do we measure our error? We measure our error by taking the squared distance. Okay? So let's say the correct answer for this image is a 9.
The brightest.
Right? So let's say the correct answer is a 9. And let's say our network in its early training stages says, I think this number is a 2. Okay? And then, or maybe another set of weights would, if we plug it in, we'll say, I think the number is an 8. Okay? Are either of those more correct or less correct than the others? Is guessing a 2 more correct or less correct than guessing an 8 if the true answer is a 9? And the answer is no. If the true answer is a 9, guessing a 2 is just as wrong as guessing an 8. Okay? As far as classifying a digit goes. However, if you have one node and you're using distance, it's going to say the 8 is more correct or less wrong than the 2. Because if the true answer is a 9, it's going to say 8 is closer to 9 than the 2 is. Okay? That makes sense if it's like, guess how much money we have in the bank, okay? And if you guess 8, you're closer than if somebody guessed it 2. Okay? That's regression. Regression says the distance matters, closer is better. Okay? But as far as digit recognition, it's a categorical thing, right? We think of it as numbers, but they're not numbers. This is a categorical, it's a symbolic representation of this kind of a concept. And so guessing a 2 is just as wrong as guessing an 8 as far as digit recognition goes. Okay? Does that kind of make sense? And so we can't use one node where we're using distance. Using one node where we're using distance as a measure, we'll say the 8 is closer to the 9. That is less wrong than guessing a 2. Okay? But for digit recognition, those are equally wrong. Okay? And so we use, if we have 10 nodes, okay, if we guessed a 2, this will be the true value is 0 and it's guessing a 1 here, and it's guessing a 0 over here. That will show up as equally as wrong as putting the true value of 1 here, where it's a 0, and guessing a 0 here. Okay, because both of these will basically, the distance here are equally wrong. Okay, as far as this vector of 10 values goes. So that's why we're turning them into 10 nodes here. For categorical outputs, you need to have one node for each category here. Okay, and so I'm going to take this, and we're going to say, okay, this first image, okay, the first image, the true value is a 5, right? So remember that first image, the true value is a 5. And so when we turn it into a vector, it's going to say these nodes are zeros, this node is a 1, and the other nodes are zeros. So this is the answer that it's looking for. It wants all the nodes to be 0 except for this one. This one should be a 1, and everything else should be a 0. And you go, well, that's the 6th node. Why isn't it the 5th node? It's because we got a 0, right? And R is 1 indexed, not 0 indexed, versus, like Python or C, which is 0 indexed. So this node corresponds to 0. This is 1, 2, 3, 4. This is 5, and then the last node corresponds to a 9. Okay, so image 5, the answer is a 9. So its last node, the last node lit up is a 9. So if I say show me digit, right? So this is the true value is a 9 here. Okay. Oh, and that's the image in our video. Okay. Okay, so we have that, and now we'll just write the code that I've written already. All right, so we saw this exact same code in our slides. Here's our sigmoid function. Here's our sigmoid prime function. Here's our cost function. And now I've just used the variables. Input layer, we have 784 nodes. My output layer has 10 nodes. And I just arbitrarily chose to have 30 nodes in our one hidden layer. Okay, and again, I know the 3 blue, 1 brown has 2 hidden layers, and just for simplicity, we just have 1 hidden layer, and I think that's fine. Okay, it's the same idea. You would just, in this structure, you would have 3 weight matrices, right? You'd have a W1 matrix from here to here, a W2 matrix from here to here, and a W3 matrix from here to here. Here we just have 2 weight matrices. Okay, I'm going to just pick some random initial weights. And so I'm going to say generate 784 times 30 random values for our first weight matrix. So that's 23,520. And I think in the code I showed you, I just said do random uniform values from 0 to 1. Here I'm going to just offset them by 0.5. So now I get random uniform values between negative 0.5 and positive 0.5. Okay, that's all I'm doing. But I'm going to take those values. So W1 is a big numeric matrix, 784 values by 30. W2 is a numeric matrix, 30 by 10, 300 random values there. Okay. I think maybe I have a couple slides to kind of illustrate what I'm doing here. So again, 784 nodes, I got 30 nodes, 10 nodes in the output layer. What we want for this first image, which is a 5, we want the output to be 0, 0, 0, 0, 0, and then a 1 for the node that corresponds to 5, 0, 0, 0. And then our guesses might give us something like 0.85 or 0.82 or 0.73. A good guess would be something, maybe not exactly 0, but like 0.001, 0.001, 0.001, 0.000. And then for the 1, it would guess something like a 0.999. And then the other nodes will be like 0.001 again. Okay, that would be a good guess. Okay, and so we want to kind of train our network so that the weights here and the weights here will give us something that gets us closer to a good guess. Now, what we're going to do is, if I tried to do the entire data set with all 60,000 images, this will bring my computer to its knees in terms of the computational power that it has to do. Okay, and so what we are going to do is I'm going to just randomly select 10 images out of 60,000. Okay, and I'm going to just say, okay, just take this tiny little data set of 10 images, 784 rows, and then find the gradient based on these 10 images. Okay, because finding the gradient is the result of doing all of these matrix multiplications, right? And so doing 60,000 rows, that's a lot. So we're going to just do 10. And then once I do those 10, I'm going to go back and I'm going to say, all right, pick another 10 rows and do find the gradient based on those 10 rows. And then take a step downhill. And then take another 10 rows, find the gradient based on those 10 rows, take a step downhill. And we're going to do that over and over and over again. So that's what this code does. It says take 10 rows at a time, randomly sample them. My learning rate here is 1. This is the code that we've seen. This does the gradient descent. Okay, we're going to just take our rows. Here I divide by 255, so they're all on values between 0 and 1. We do forward feed to get our predictions. Once I do forward feed to get our predictions, I figure out our gradients. And then once we figure out our gradients, we take steps downhill. And that's it, right? So this code, I hope, doesn't feel uncomfortable, all right, as far as what are the operations happening. So I run this. It's going to take a couple of seconds. And it's going to go through 10 images at a time. I think I ask it to do it 6,000 times. All right, and now it's done. Now it's done. Okay, we have trained the network. We have found a set of weights, W1 and W2, that we hope gives us good predictive performance. So now we will take our test data that we've never seen before, and I'm going to have it produce the guesses using forward feed. So I'm going to take all of these things, and the guess will say, all right, like if we look at, actually, let's just look at this first row here. Okay, this first row looks like this. Let me round it. Okay, so what guess does this correspond to? I got 0.002, 0.000, 0.0024, 0.002, 0.0000000000000, 0.9998, 0.0000, and 0.001. So this corresponds to a guess of 7, right? It's the 8th column, which corresponds to digit 7. So our guess here would be, I would take this, basically take this thing And we're going to ask, what is the max column? All right, whoops. Max column minus 1. And so anyway, so these will be my guesses. Okay, so our first guess is a 7. And what does the digit look like? Yep, sure looks like a 7 to me. Okay, so that's it. Like it's guessing, right? All right. What about the next digit? Okay, the next digit, it's guessing a 2, and yep, the digit looks like a 2. The next guess, it's guessing a 1. There you go. It looks like a 1. Okay, it's guessing a 0, and that's the answer here. Okay, so we can create what we call a confusion matrix. And I can compare the actual values versus the guesses. So this is our confusion matrix. What we want to see is we want to see big values along the diagonal. That's where it got correct. So the actual value is a 0. It guessed 0 941 times. There were times where the actual value was a 0 and it guessed a 2. And there were times where the actual value was a 0 and it guessed a 6. And we can kind of understand that. All right. Here, the actual value was a 1, and it guessed a 1 1,113 times. Sometimes it made mistakes, okay? You know, it struggled the most with 5s, it looks like. When the actual value was a 5, sometimes it guessed a 0, sometimes it guessed a 1, sometimes it guessed a 3, sometimes it guessed a 5, sometimes it guessed a 6, things like that, right? So we can look up, like, where do we make mistakes? And these are some of the indexes where it made mistakes. It made a mistake on image 9, made a mistake on image 16, right? And so it made mistakes. It made 749 mistakes out of 10,000 images. So we're getting an accuracy of around 92.5%, which is not bad for our very simple neural network. And again, I don't know if you'd had heard about neural networks before. I imagine you had, but if they might have seemed like this mysterious black box thing, okay? And I'm hoping that what we've done today has shown that, oh, we're just multiplying matrices, okay? It's not super weird and mysterious and complicated. Yeah, there's a lot of computation involved, but we're just really multiplying matrices together. Okay, and that's all it is. And if we can do this, then we can make really big neural networks by just multiplying bigger matrices or more matrices together. And if you have these big neural networks, then you can start predicting images. And again, it feels mysterious, but really it's just put some numbers in, and it goes through the thing, and it spits a number out. Okay, let's take a look at some of these mistakes. Image 9 was a mistake. The true number was a 5. It guessed a 6. All right, let's take a look. Oh, we go, okay, yeah. And we go, I don't blame you, neural network. This was bad handwriting, right? So the neural network guessed a 6. I think we look at this and we go, yeah, I can see how that's a 5, but also I can also see how the neural network thought it might have been a 6, right? Here, the true value is also a 5. It struggles with 5s a lot. It guessed a 3. Let's take a look. Okay, all right, that looks like a 5, but we can also say, yeah, I can kind of guess how you might think it was a 3 or something, okay? And you can kind of go through, you know, some of these other mistakes. What else was a mistake? 1635, let's see. True value is a 4. It guessed a 7. Okay. Yeah, it's a 4, but we're also not super angry at the neural network either. Okay, and so the neural network right now, you know, not the greatest performance, 92.5% accuracy. Obviously, your mail would end up with lots of problems if we have that, but this is again a very simple neural network with just one hidden layer and 30 nodes. And if you make your neural network a little bit bigger, a few more layers, and there's a few other things you can do to improve neural network performance, you can get really good accuracy. And so, so today, the post office system for handwritten mail is really, really, really good. And it only has to handle like the tiniest percentage of handwritten mail has to be kind of manually processed, and that's that. So anyway, and then yeah, again, your phones now have kind of brought in a lot of this power, and you can take images, and then your phone is now able to kind of scan and say, oh, these are pictures of bridges, and these are pictures of dogs and stuff, right? You ever use the search feature on your phone? When you look at your pictures, you can kind of just go in and say, within the library of photos that I've taken, show me pictures of a bridge, and it will find images of bridges in your thing, or things that resemble bridges. It might just be pathways, but that aren't real bridges. But it's trying to guess these types of things, and it's all kind of powered by neural networks in your thing. Anyway. That's it for today's lecture. Let me give you your last view quiz answer. Today's last view quiz answer is the letter B. B as in bear. B as in bear. B, okay? And I've posted the code that I've used today on Canvas in the modules. And so my hope is that it'll be kind of interesting. You'll have to deal with it when you do your homework. But that's that. Okay, good luck as you study and prepare for the midterm exam on Thursday. So we will see you Thursday at 9 a.m. Make sure you bring a calculator. Also bring your note sheet. Okay, don't forget your note sheet. You're all allowed a page of notes here. Okay, we'll see you on Thursday. All right, have a great rest of your day.